Yeah, so first, thank you very much for Massino and Queen Mary for inviting us for giving this presentation on talking about a bit how do we apply AI in news filtering. My name is Raymond Ng. I'm from Signal AI. I work as a data scientist there. A bit about my background. So I did research in speech recognition in University of Sheffield before, and then speech is about different applications and automatic processing on the acoustic data. So use cases include speech recognition, voice print recognition, or recognizing the language from the acoustic form. And one particular project I was involved in is spoken language translation. So that hits a bit of NLP, and then there I moved to Signal AI doing proper natural language processing stuff. So in this talk, I will talk about our methodology and philosophy in how we process the data. So I will use some examples and use some deliver high-level concepts in machine learning. Most of these concepts are familiar to all of you, I'm sure. But I will try to explain how we use these concepts and use the divide and conquer principle to just tackle our problem. So a bit out of our company. Our company basically focused on media monitoring, reputation management, and market intelligence. So in case you don't know about these buzzwords, these are the functions for business and companies. So when I start a company, I have a brand. I want to know how my brand is perceived by the society, by our competitor, and more importantly, by our potential customers. So we provide service to these companies. We try to harvest all the data available online or subscribable data, primarily news data, and then extract information about branding, about reputation, and deliver these information to customers. So we were founded in 2013 in London. We started in a very small garage and then just built proof of concept system, prototype, and then now we move on to deliver comprehensive solutions to hundreds of different customers, both in the UK and internationally. So you can go to our website and then you will see a list of customers. Some of them you can see their names, and some of them you can't see definitely, but then there has a wide range of different customers in our customer base. So we successfully raised a few rounds of funding, and then our commercial achievement is recognized by different commercial awards there as shown here. And from last year, we just expand beyond the UK and open offices in New York and in Asia this year. On the research side, as Massimo introduced, we worked with different universities. So we worked with University Essex in knowledge transfer partnership KTP projects, and we also work in tens of different research projects in different areas you can think of about NLP on news. You will see a bit of these examples in the later slides. So in today's presentation, basically, I will try to introduce our use case in news filtering, and particularly focusing about the challenge. You may see this from the abstract I've written. So how we deal with a lot of data, how we deal with these data in a quick manner so that we can deliver real-time solution to customers. And then to pinpoint specific challenges we have and try to use just all the machine learning and logic and knowledge we know to just handle these problems. And in the end, I will try to show you like how we work and then what's our achievement. So that value pyramid will just highlight our philosophy on how we understand the problem. So basically, the problem is to work with a large amount of data and to extract useful information and to deliver value to our customers. So we have in the base layer and aggregation layer, which emphasize on collecting complete and large amount of information in real time. Here we're talking about different multiple media data types, including printed news, broadcast news, blogs, regulations, etc., etc. And all these will be potentially relevant to all of the customers or some of our customers, but no matter how interesting or how much interest these data are, we want to have full comprehensive coverage of these data so that it will be available to our customers. And these should be available in real time. So after we have harvested all these data, then we move forward to the monitoring layer. We use information filtering to do document-based filtering so that we can select a subset of documents which are relevant to each of our many different clients. So these monitoring or filtering are achieved based on complex queries, and I may show you in a while some of the screenshots of our system showing how user will be able to interact with the system and to get relevant information from the large amount of data. And then moving upward, then there are different machine learning modules doing entity recognition, topic recognition, or sentiment, quote detection, etc., etc. And these will explore informations and add value to the data in like high volumes quickly. And we also focused on how to deliver the information effectively to user. So if we have a machine learning model which gets information or give a particular annotation to particular target classes we're interested, is utmost important for us to be able to deliver this information to the customer in a very efficient way so that when user log in our platform, they will immediately see what they need. Also, because there are so many information we extract, so how these different informations interact with each other, and what about the trends, the changes over time, and comparisons of different informations, these will also provide added values to our customers. So with all these data and derived information, we also have domain experts to discover the information and provide systematic factorization, recommendation, and scanning of the data. So these will give useful, inspiring insights to each of our clients so they can make informed decisions to their business strategy in predictive modeling, forecasts, or like long-term development on their company. So that's how the life cycle of using the data in benefiting a business. So a bit about the actual challenge there. I have already mentioned a little bit about the scenario, the user scenario here. We have to process a large amount of data. The data here we focused on is openly available data from news, media, or subscribable data in the news. So we're talking about around 3 million articles per day, so that is a vast amount. And we have to have a resilient system to be able to process all these documents in an accurate way without error. And also we have to deal with the spike usage because these documents do not come into our system in regular time interval. Sometimes when there are spikes, there will be hundreds of thousands of documents coming in within an hour, and then we have to be able to ensure our system is able to scale up itself so that it can handle all these spike in a proper manner. So we cover different data sets and data sources so that we will try to have a complete coverage of data. So inevitably, these data will come from different sources. Different news sources, you can think about different formats, so there will be some glue issues, input-output formatting you have to handle, and there are also different copyright and law limitation that we have to comply with for each of the data sources that we are handling. Because we serve customers who are international companies, they have presence in different countries, and then it's important for us to deal with sources from different geographical regions. But also we think it is important for domestic business to have a view on some of the data outside their own country. This is because big news which is happening in the world, or user preferences, or sometimes law enforcement trends. So these things normally spread from country to country. So when we have an FDA regulations to try to control or to regulate some of the chemical ingredients or drugs in the States, so this news may spread from one country to another, then it will be good for business to be able to capture these trends from data as early as possible, even these trends do not happen in their own country yet at this moment. So the next challenge we have is obviously speed, because we are talking about a huge amount of document per day. We have to processing them real time. So it is important for us to consider a design which is seamless, a very smooth pipeline, deliver all the possible actions that we want to do, yet doing a real-time process, not building up a lag or latency. The third challenges we have is customization and quality. So I've just mentioned we have hundreds of different customers, and each of them have slightly different requirements. So some of them may need to view particular items or topics about their companies, and some other clients, they work in different protocols, so their workflow will be different. So all these tiny difference will have to be catered in the pipeline to ensure that the customers will have a very good or satisfactory experience when they use our platform to harvest information from the data. Then this is a bit about what I just talked about, how to make users happy, basically. So we have the AI system, which does all the machine learning process, harvest information, add value to the data. But then how do we effectively deliver that? So the two principles we follow is to enhance data accessibility. So if you have the data there, how do we allow user to search over the data in a very quick, efficient manner without any delay and without any confusion? Second is about insight. So you have a lot of different information. You have the curve of trends and distribution of source across different geographical regions, or some of the topicalization across different data sets, and how to organize them in a nice way, and also combining different useful information together. It is very important and valuable way if we are able to compile this information effectively. So with all the background here, I hope it was not too long and too boring, but now I'm going to move onward to give some of our machine learning insights. So I'm just trying in this section to give some high-level concepts of a machine learning model, which I'm sure all of you will be familiar about, and then how we apply these concepts on to the problem to deal with the challenges I just mentioned. So a very classical definition of the problem, because this is an text analytics problem, then we start with text, obviously. We define a document D, which is a sequence of tokens or words containing many different words. And then output formally, it is defined as a decision, normally solved decision given by an automatic system, indicating the likelihood of the document is sampled from a probabilistic distribution represented by a model. So a concrete example of that is topic classification. You build a model for a specific topic, and then you run the probabilistic model, you feed in the data to that, and then it gives you a solved probability, and then you decide what to do, accept the topic or reject the topic based on this solved decision. Another example here, I will go through that, which is summarization or tagging. So you will have, at this time, a much higher temporal resolution of output because you input some document or word sequence into it, and then the output will be some of the tag sequence. I'm trying to put all these different things in one single generic universal framework here, so to facilitate our discussion later. In the process, we benefit from making use of different information sources, for example, knowledge base or some of the pre-trained model. That will be very helpful, but then there is a caveat, because in some of the cases when we didn't use this pre-trained model in an appropriate manner, that will actually bring us harm rather than benefit us in having a good solution. So the standard way of evaluation, we use a hello set of evaluation documents, generate some predicted outputs, and then compare these predicted outputs to the Oracle outputs to see the level of accuracy and matching between the Oracle and the prediction, and to have a correctness judgment. So this is just an example pipeline which I tried to fit in different machine learning module into it to illustrate how we process our text. So on the very left of the pipeline, you will see the data, the sequence being fed into it. It can be printed news, online news, or documents, or even broadcast, then data cleansing module will be responsible for formatting, and then it gives you an analogous sequence, but with all the noise and nonsense tokens or nonsense bits being removed. Summarization will give you a shorter sequence, which semantically, ideally, it semantically will match the same to what you have in your original document. Duplicate detection seems to be a very trivial task. In micro scale, then you pick pairwise documents or group-wise documents, and then you just exhaustively compare each of them to see and to try to pick groups which have low or zero edit distance, and then you say, oh, this is a duplicate, and then you pick this out. The reason we want to do duplicate detection is to just alleviate the pressure in the downstream pipeline, because in our data ingestion, there will be news articles which is repeatedly fed into the pipeline. So if we don't do that, then we will have wasted a lot of processing effort, because basically we are processing the same thing. So I was talking about how trivial it is in a micro scale, but then think about that, we are processing millions of documents a day. So whenever we receive a new document, we have to compare each of the new document with millions of the document in the database. So it is proved to be a really challenging operation there, how to deliver a sensible, efficient, and also accurate solution there. So here we use some kind of probabilistic hashing to make sure the solution is acceptable and at the same time efficient. And then there you will see different modules running: entity linking, topic classification, sentiment analysis, and quote detection. So these will be just very standard supervised learning modules. When you feed in the data sequence, you train a machine learning model, sometimes even rule-based mapping, and to give you either hard or soft decision, and then you decide what to do with this decision. There are some interesting facts that we can play around with all these different modules in the pipeline. First, we can try to see how we can link different modules together. For example, I talk about duplication, linking the downstream ML. So if we take this hierarchy of a machine learning module, inputting document, outputting some decision, there, then we feed the output decision into the next module. By doing so, we will be able to save a lot of computation resource actually. And the second example here is that we can try to build the machine learning platform in a way that we will have different branches, different forking, different combinations of connections between modules. We can design a route where we link both raw data and summarized data into one of the machine learning module. The reason being that you will have multi-view, different view of the information, and you can combat the problem of sparsity just because you have multi-view. Also, in an information theoretic point of view, then you may want to link different modules together. So for example, sentiment analysis, entity linking, you may want to do entity-based sentiment analysis, just because you want to model sentiments conditioned on entity, and that gives you a higher accuracy or more robustness. So these are the different ways we can play with once we have this complete system up and running, because you can draw lines between different modules and then try to link them in different formats, and serving one of the few purposes I mentioned, to save computation time and resource, or also make the prediction more accurate. So this is just another view of how we construct the machine learning pipeline here. Again, we have this input D and then a big module here and derive the outputs here. We are all familiar with natural language processing operations. So one of the important procedures here is feature extraction, because we deal with not only the raw form of the text, but sometimes the TF-IDF features, or nowadays embeddings or contextualized distribution representation. And these actions, we consider them as feature extraction. So I just casually put a feature extraction module here inside the middle block. Then after we extracted features, then we perform a standard inference procedure. We normally will transform the data and then feed into a probabilistic model and do inference. Example output include embedding, domain-dependent information, or task-specific prediction. So I put embedding here for a reason, because some people will regard embedding as a feature extraction process, because what you're after is just a continuous representation of your word. But then think about how we extract our embedding. So we take a pre-trained model, and sometimes we do fine-tuning, and in more classical examples, you will see tandem system where you have a first huge network doing these embedding extraction, and then you feed the embedding to another network serving your second task. So somehow these embedding or feature extraction procedure looks a bit like inference of model probabilities. So here, since I am delivering that in an industrial or commercial point of view, so I think I can be allowed to casually blur the distinction between feature extraction and the inference of model parameters or model probabilities here. There is a reason for that. So now I'm going to talk about exactly how we're going to tackle the problems. So the first way we try to deal with the quantity issue is to have hierarchical models. As we've mentioned, we have a lot of different customers and there are different use cases. So there is a need to deliver the solutions particular to each of the interested customer and interested use cases. Then you can think about building specific, independent, individual machine learning models serving single purpose, one at a time. But then a hierarchical model will serve the purpose of using a shared model upfront, and then it delivers some kind of high-level information or inference in the first level. So normally this will be computational heavy. And then after that, you will move on to the next level when you employ some downstream model and try to use it to deliver specific and fine-grained information. Now these downstream models, normally they are very lightweight and they operate very quickly, and they are adaptable. So by structuring the hierarchy like this, then we can save computation resources in most of the cases. I talked about the casually blur of between model parameters inference and, the model probability inference and feature extraction. So here this is another example for that. So you can have a hierarchical model, and you can even have different feature extraction. So you will have upfront feature extractor extracting your embeddings, and then using your embeddings, which is trained for different but related task for your downstream task. Then you can reduce your computation load in the downstream layer. But there is a caveat here. So we have to avoid having a sticky cascade. That means by having such a hierarchy, so it can be anything. You can build a model to classify a class of, say, transport companies, and then you have another model to classify individual transport companies. But by doing so, we are implicitly injecting some relation between the type of transport companies and individual companies there. So it's most of the cases it is fine if we know what we inject is probably static and is not going to change. But if in that case, if we're going to relate different customers, which happens to be very fluid, or they will change their name, or they will change their relationship a lot of the time, then the change of individual model will affect the whole chain, and then that will give a negative effect on the whole system. And that's something which I refer to as sticky cascade, and we have to be aware of that. Secondly, it is about the use of data. So we talked about in the filtering level or monitoring level in our pyramid, which is about selecting subset of data relevance to particular customers in our huge customer base. So here it is more about selecting particular data for training particular model. I'm just quoting some classical knowledge from like the machine learning textbook in Chris Bishop about rejection sampling. I think most of you know about that. So just to highlight that it is easy to compute the probability for distribution, but in most of the cases it is quite difficult for us to sample a data subset which follows that distribution. So what we do here is we propose a surrogate distribution which we can easily sample. Here it is a Gaussian distribution, and after that we repeatedly sample the data and then try to compare the actual likelihood between the surrogate distribution and the actual distribution. Now when we're at this point, when the two likelihood are the same, then we keep all the sampled data. But if here our actual distribution will give half the likelihood of the surrogate distribution, that means we have to throw away half of the data we sampled. So by doing that repeatedly, we started with a surrogate distribution, but then we have a data set which follows the actual distribution of our data. I just want to emphasize that particularly because this is one of the use cases which we normally didn't see in academic research or when we use open data sets. So we normally will extract or we'll source the data, and then we assume these data are properly distributed, and then we will compute statistics on the data, and we rely on that. But this is not the case in reality, because we received source data from all different locations, and then there are duplications, there are skewed distribution. So it's very important for us to correctly sample the data and to get the appropriate representation of data so that the inference from our model and conclusion drawn from that will be correct. Of course, when we talked about a large number of data and also the speed of processing, then we have to ensure these inference or feature extraction will be fast. One classical, typical method you can use is feature selection or dimension reduction. So you can use PCA or LDA. LDA as in linear discriminant analysis to do dimensionality reduction, so your problem space will be smaller, so that processing speed will be faster. Then we can compress the model, obviously. So you can compress the model in machine learning way. I have seen paper outside just about doing teacher-student training, and this is actually a very popular topics in different areas in speech, language, and also computer vision. So you train a teacher model using a lot of your data and large network. The reason you want to use many parameters to train your teacher network because your data is not clean, you may have wrong labels in your data, and also your target, sometimes it is not smooth, so that you will need extra parameters to do all these factorizations. But then once you have the teacher model there, what we can do is the so-called knowledge distillation, to distill the knowledge from the teacher network to the student network. So there are some works in some of our problems, our in-house, that prove teacher-student learning can be very effective if you stay in like in-domain data with you don't have a lot of domain mismatch between training and testing. You can easily achieve like 90% of parameter reduction with like your performance almost retained the same. Finally, of course, there are some engineering tricks you can apply to reduce the size of the model. You can do parameter encoding, quantization, so you can just use the numerical accuracy sufficient enough to decode the actual results, like fixed point operation that will speed up your computation. And all these different engineering tricks and techniques will be important. So bits by bits, we apply different methodologies and add up together to ensure our pipeline will be delivered in real time, so that the customers will be able to get the inference from these documents very quickly. So more about speed, you may already be able to figure out what I'm going to talk about here. So just look at different steps in the pipeline to analytically sort out what are the actual time being consumed in different procedures. So input, output, how much time do you spend writing data in the disk? Can you spare this time by having less I/O, just using more cache memory? And also, how do you load the model? So can you set up a server which you preload all the models so you will save that bit of the time? Can you do transformation of features upfront so that you don't have to do that repeatedly in case you need to feed the same features to different models in different time? How about inference, calibration, and are there any tricks that you can speed up computation? So we really think really hard in each of the procedures and operations, and then apply any tricks you can think of to ensure the pipeline is fast. Customization. So we have a lot of customers. I repeatedly mentioned different customers have different requirements, and we have to make sure all our customers are happy. This is just an example from the Track Web 2010 topics recognition. So we plot a histogram of the average performance. So this is the average precision, and then there are different topics. Then here you show the number of topics which end up having this region of performance. Then the single message here is that we have some topics behave relatively well, reasonably well, but then there are a large number of topics which also doesn't behave quite well. In system evaluation or quality estimation, we sometimes focus on the mean or average performance of a system across different classes. But here, we don't have that luxury, so we have to go into each of our target class. So if we assume each target class will deliver a solution for each customer, and to make sure that each class will behave well and satisfactorily. The tricks we applied include like some small tricks like regularization, calibration of our system, and we may also need to use hierarchical ensemble model just to improve the discrimination power of particular class when this happens to be difficult. One point we also spend a lot of time on is to make sure the label quality is satisfactory. We actually also see that in open evaluation when I was doing speech research. So when we participated in a NIST evaluation, the National Institute of Standard and the Standard, they try to organize evaluation to ask people to evaluate audio clips and to decide what language they are spoken. So there are many teams, tens of different teams sign up these evaluation, and then we run system recognizing different languages. So it turns out that all of our teams have troubles recognizing one particular language, and we are all confused about what's happened there. And later, after the workshop, we find out there are annotation error, because it's always possible that in this situation, when we are talking about, for example, minority language, when expertise may not be readily available, so in particular situations, the labels may not be the absolute thing we have to trust. So in some times when there are problems in the annotation procedures, we may have to go back to the whole annotation step to relabel the data, retrain the model to improve consistency and quality. There is one final bit about proper evaluation that I just want to highlight. I'm trying to illustrate this using a toy problem by plotting a precision and recall curve. So I show you the precision and recall curve for 3 different systems. You have the performance of one system here and the other 2 which are closely aligned with each other there. And then as you see, we change our detection threshold and you will have the whole operation characteristics curve. Of course, here you will have a very high detection threshold, meaning you have a high precision because you reject everything unless they are of really good quality. Then you have a high precision but a very low recall. And as you lower and lower your detection threshold, then you accept more and more, but you also have more false positive, leading to the reduction of precision here. And then you see different colors of the points because we vary different detection threshold. So the point I want to make here is that these simple graphs and analysis will prove to be very important for us to understand the system performance. Sometimes we use a very simple metric to quantify and to have a feeling how good a system is. For example, we just looked at precision and recall at a particular operation point, normally here in the middle. But then in most of the cases, actually, we have to look at the whole curve to see how these precision and recall or criteria interact with each other before we can come up with a conclusion whether the system is good or not. So, of course, you use area under curve and then average precision or precision at 20, etc., etc. So these different metrics will interact with each other, and in a case-by-case basis gives us different qualitative conclusion on how good the system performs. So I mentioned about not relying on single operating points, so we have to look at the whole curve. The second is about the sensitivity of the detection threshold. So normally, in a detection system like this, you will put a 0.5 threshold, and then to accept or reject your classification results based on whether your score hits above or below the threshold. Then these thresholds will lie roughly at this region in the dark green and light green color. That happens to be a quite nice scenario, because when you vary your threshold from 0.5 to 0.7, you don't happen to have a large variation of precision and recall, which means that most of your performance changes happen in the high threshold region. And if you try to plot the histogram of positive and negative distribution, you can easily imagine that you have a lot of positive example distributed densely in the high score area, and that was constitute the wide area of purple dots here. So this is a second system where actually I'm more happy about, because in the first glance of the system, you may see, oh, this is bad. You have a very low precision here. But then when we look into that in more detail, you can see this low precision actually happens when you have exceptionally low threshold, 0.1, 0.2. And in most of the case, you won't try to push your system to that extreme threshold. And that means this area of the curve is basically meaningless. You don't have to exploit that area at all. Compared to that, so if you use some sensible threshold, so you will still hit the area of low precision, and then when you move to like having a threshold of 0.3, you may already have a precision of 0.7. So these very deep insight of how we analyze the system is proved to be some of the important knowledge which we all know, but due to time pressure or sometimes due to just when we overlook the system, we will miss these, and then affects the overall performance in the system. The other challenges I mentioned is user interaction. So we have talked about our machine learning system, which derives different information, and these informations can cover location or organization, person, and also different topics. So it is very important for us to combine all these different fields together, as I've mentioned, so that you can have an augmentation of the knowledge discovered by the pipeline, so that the user will be able to benefit from it. I was going to I'm thinking trying to spend some time on embeddings and data, but I'm almost running out of time, so I'll try to go through it quickly. This is what we all know, so we use word factors, and then we benefit from that famous example of king minus man plus women equals queen. So that is the idea of distributed representation, and then how that solves the sparsity issue, because you will have a distributed representation which represents many different data in your data set. So you won't end up in having a lot of sparsity, and you can have a better generalization power. Of course, then you move to contextualized distribution representation using BERT. Then you will even gain more by using these so-called pre-trained model or clever intelligent representation. So I'm sure all of us know about how to implement these and the methodologies behind. Just to highlight a couple of learnings there. So these state-of-the-art techniques, we employ these in different bits in our pipeline. But what we discovered is sometimes we really have to do sensible and fair comparison between what we employed here and our baseline benchmark. So we will only employ these state-of-the-art methods when we think, okay, the performance gap is really huge and then it is worth doing it, because in most of the time we will notice a substantially higher computation requirement in these methods, and also at some cases there will be task mismatch, particularly when we talked about employing some pre-trained model and to apply that on a different transfer learning task. And then more about the data. So you may remember I talked about the importance of deduplication and to derive the weird distribution of data. This is just another toy example when we try to run an experiment in an irresponsible and nonsense way by blindly feeding data into a neural network and let it train. Then you will see the training loss suddenly decreased to 0, and then it just fluctuates crazily. This is the reason of having a heavily duplicated data. So when the network learns something, we thought we have been feeding 1,000 data points to the system, but actually because they are heavily duplicated, then it just learned a particular feature or representation which is occurring in 500 data points out of the 1,000 data points we are training, so that it quickly drops here, and then in the next iteration it goes up because there is a slight fluctuation of some small features, so it fluctuates again and again. Of course, you can argue, you can use regularization methods and parameterization to try to detect this issue, but then we will say if we can detect these issues from the very beginning with a more intuitive and simple method, so why not do that upfront by pre-process the data cleverly, in a clever way. There is a consideration about generalization power and data homogeneity. If we are only focusing on designing a model or some advanced machine learning techniques, of course generalization power is what we are after, and then we try to build a very strong model which will tackle different cases when training happens in this data and then testing happens on a completely different set of data with very different mismatch issue. But in application, we can think about the problem in the opposite way. If we have ways to guarantee that we have a minimum training testing mismatch, that will be a quick win, because what we train from the model will not suffer that much when we apply to the test. And actually, there are lots of practical measures that we can adopt to ensure the homogeneity of data between training and test. Finally, another quick win for the efficient use of data. So I briefly talked about the label quality before. So this is just about active learning. So I'm quoting another paper from Settles in 2010. When you train your model, you label that, you build your model, and you evaluate your data to see what's the problems there. Are there problematic labels, problematic samples? Are there any particular area in the feature space that you want to focus in? If there are, then you focus on that, relabel that, and then you reiterate the training process. Because here we're not talking about having constrained data. The only criteria or objective here is to improve the model performance. So we can do whatever we like. We can harvest our data, we can use crowdsourcing or some proficiency annotator so that to improve the quality of the data. So finally, it's just a very short description and gives you just a sense of how we achieved in the area. So we run different operations like text analytics task, and example task on entity linking that we are proud of. We delivered an F score of 0.96, and that's subjectively is converted to some very satisfactory client experience. So that's why our client base keep growing. We have very resilient system infrastructure. I didn't tell you what exactly we've done, but I think from the talk I've mentioned, we just describe all these different techniques which are openly available from the academic publication, and you will have a sense what we did to try to ensure a resilient and robust pipeline. And this pipeline is very established, so we actually fulfill some requirements of large corporate customers because they have standard requirement on procedures and protocols that we have to follow to make sure that when they enroll to our system is robust enough to serve their needs. Real time, so we can deliver real-time ingestion and annotation of the news article, and we have continuous growth year by year. Also, in terms of headcounts, we grow from 50 to more than 140 in the past year, and we collaborate with different universities. Massimo's group, previously in Essex and now in Queen Mary, and the groups in University of Sheffield, City University of London, particularly with the journalism department, and also the University of Duisburg-Essen in Germany. So finally, just to give a short summary of the academic collaboration we are having. So we are constantly hosting visiting researchers. We're actively involved in different master projects, and we have PhD visiting interns working on different exciting problems on NLP. We're involved in publications, and also we organize academic conference and workshops. So just in July, this July, we host News IR, so which is a workshop to look into the interaction of journalism and machine learning text analytics. This is an affiliated workshop with SIG IR, and this is a huge success there. We also have organized meetup called Search Solutions, and also other meetup meetings. And we try to contribute to the research field by providing publicly available data sets, which is called Signal 1 million, so it contains 1 million of news articles. If you're interested in more details, do talk to me offline. And we are actively involved in the KTP projects as well. So that's the end of my presentation. Thank you very much.